Hello everyone. So good morning. Let us start with the lecture 11. We were discussing Bayes theorem, and we will do more problems in Bayes theorem, and then we will define something called independence. So last time what we were doing is Monty Hall problem, and this gave you some idea of how Bayes theorem can be used in the Monty Hall problem. We saw a variety of ways to solve Monty Hall problem, and in this problem we saw that the fact that Monty reveals a goat door always changes our intuition drastically. So when we switch, then we increase our chances by 1/3 more. Okay, so our chances of winning the car became 2/3 when we switch. So that strategy helps. The fact that Monty always opens a goat door, that is the most important point here. And if Monty opens a door randomly, then things will be a bit different. Okay, so if we look into the conditional probability calculations that we did, okay, if we look into that, then what we had was, if you recall, then what we had was this. So we defined events H, where event H means that door 1 has a car behind it, and then another event we defined was E, which means that Monty reveals a goat door. Okay, that means a door he reveals a door containing the goat, and then we know that probability that the door 1 has a car behind it, it will be 1/3, and probability that it won't have will be the negative 1 minus of this, so this will be 2/3, and probability of E given H. So probability of E given H means like probability that Monty reveals a goat door, given that that door 1 has a car behind it. So this is like certain, still it's 1. Okay, because there are 2 goat doors left, so for sure it is still going to with a probability 1, it's going to be a goat door, and probability of E given H complement. Okay, this is the tricky part. So what this means in words is like, what is the probability that Monty will reveal a goat door, given that door 1 does not have a car behind it, which also means that that has a goat behind it. Okay, so what this means is like Monty, I mean door 1 has goat. So this is given to you. So door 1 has a goat. Then what is the probability that Monty reveals a goat door? Now how many doors are left? So the door 1 has a goat. Now that is given. So now what we are left is goat or car. So now Monty has to choose out of 2, and since this is a random Monty, so he is not surely going to open the goat, right? So now he has to, it's like a coin flip, so its a probability is half here. Okay, so this is why this is the only thing that changes, okay, in the random Monty. If it was not random, then this was still 1 for us. Okay, so that's the change that we are trying to do. And if you do all the calculations and so on, I'm not going to do all the calculation again. You will find that it is indeed half. Okay, so the probability that door 1 has a car behind it, given that Monty, if Monty randomly picks a door, then your probability of winning a car, it remains half. Okay, and obviously in this case, like either you switch or don't switch, it doesn't matter. It still remains half. So in this case, the strategy, okay, for you it's like doesn't change. So if I switch, then it will become like this. Again, it's half. So if if Monty reveals a door randomly, then it fits in our original intuition that that it's a 50-50 because yeah. So the fact that Monty reveals it in a deterministic way, only the go door, that's why our intuition fails, okay? Or the usual intuition fails. If you think hard, then it's still makes sense, okay? Why it should be 2/3. Okay, so this was random Monty, okay? Now let us go ahead and do some more problems. Some problems in probability. So let us say, or probability in the sense like classical probability. So we are soon going to get out from classical probability. From the next class, we will start something called random variable, and that's when you will see a lot of interesting and modern ideas. Okay, so let us see this problem. On the morning of January 1st, a hospital nursery has 3 boys and some number of girls. Okay, on January 1st, so we can make a timeline. Okay, so Jan 1st. Okay, so on Jan 1st, what it says, it has 3 boys and some number of girls. So 3 boys, okay, plus some number of girls. Okay, so some number of girls, like n number of girls. Okay, and that night a woman gives birth to a child, and the child is placed in the nursery. Okay, and on January 2nd, a statistician conducts a survey and selects a child at random from the nursery. Okay, including the newborn, obviously, and every child from January 1. Okay, then the selected child turns out to be a boy. Then what is the probability that the child born on January 1 was a boy? Okay, so what is the probability that the child born on January? So let me sketch again what is happening here, just to see what is happening here. Okay, so there is a timeline. Okay, so there is January 1 and January 2, right? So let us say event January 1. In event on January 1, what was the situation in the nursery? There were 3 boys and some number of girls. Okay, so let us say k a number of girls. Okay, that night a woman gave birth to a child, and the child is placed in the nursery. Okay, so here one child was born. Okay, so we don't know which. Okay, oh yeah, so it's just one child, whether it's a boy or girl we don't know. Okay, so there was one addition, one child was born here. Okay, and then so this child still remains in the nursery on January 2nd. So we move to January 2nd. On January 2nd, a statistician conducts a survey and selects a child at random from the nursery. Okay, so this is the situation right now. It's either 4 boys and k girls, or it's 3 boys and k plus girl, 1 girl, because this child could be either a boy or girl. So on January 2nd, the statistician will pick some child at random, and he finds that he selects a boy. Okay, so statistician randomly selects a boy. Okay, and this is also important, randomly. Okay, so statistician selected a boy, selected a child, and it turned out to be a boy. Now the question is, what is the probability that the child born on January 1 was a boy? Okay, so what is the probability that child born on January 1, which is this? So there is a timeline here, like January 1 something happened. Okay, and there was an increment. on January 1, that increment is not known. Okay, that increment is not known. And then on January 2nd, one picks a child randomly, it's a boy. Then what is the probability that the child born on January 1 must have been a boy? I mean, yeah, would have been a boy. So this is the problem. Okay, yeah, so we want to use some whatever we learned about probability, right? It should be conditional, because conditional is natural here, because it's all about like, given that the statistician has selected a boy, then we are talking about the child and so on. So this is indeed a conditional probability and so on. Whether we need Bayes and so on, we have to figure out. Okay, what is given in the question. Okay, that will determine whether what are the things we need. Okay, whether we want to exploit total probability and so on. So as usual, one thing that I will always recommend is drawing some kind of tree diagram when solving problems like this. Okay, tree diagram really helps. So the way you will go about solving this is to form a tree diagram. So let me do this solution here. Okay, so what was the situation? We had three boys and three girls, okay, to start with. And then something changed after this, right? So there were three girls. So there are like cases now, right? So one child was born, so there was +1 here. So there is like three girls, and let us say 4 boys. Okay, so let us say that it was a boy branch. Okay, so this is like a boy branch, and then this is like a girl branch. So 4 girls and 3 boys. Okay, so these are the possibilities we have, right? So tree usually helps in counting these possibilities, right? So if this was the case, then the probability that probability of selecting a boy from this branch would be like the branch is like 50-50. So this goes in a half way. So it's like half of choosing this branch, and if I am focusing on the boy, selecting the boy only because the question is asking for that. So then if indeed the increment was a boy, then we had this 4 out of 7. Okay, so once I come in this bin here, selecting a boy is like 4 out of 7. And if I come here, then this branch is half, and then it is like 3/7. Okay, so if we define an event, let us say define an event. Let us say we define an event B, which is select boy. Okay, so selecting a boy. And let us say we define the event N is that newborn is a boy. Okay, newborn is a boy. So we can write B as a, how can we write B? We can partition B over this, right? So we can partition B. So we can write B as B intersection N. Okay, and the union of B intersection N complement. Okay, so you take everything that intersects with N, or you take everything that intersects with N complement. So overall it will be B, right? And these are like mutually exclusive. Okay, so now probability axiom says that I can write this as probability of B intersection N plus probability of B intersection N complement. Okay, so if we do a calculation for this, so this was like so now we will look into the tree and figure out, right? So B intersection N, so what is this, like B intersection N? Okay, so can you tell me from here? So can you tell me like what is B intersection N? Yeah. 4/7. Yes is saying 4/7. Achilles is showing 4/7. Mehul is showing 4/7. Why did I number of girls? Okay, good question. Why did I check number? Why did I take number of girls to be 3? Actually, I forgot to tell you. Like I start with some example. Okay, so assume. I will generalize this. Okay, sorry about that. I assume that there are 3 classes. Just getting an intuition right now, but I will replace it by K. Okay, later on. Okay. Okay, Rahul. Okay, so it's clear. So yeah, so you're right. So this is like probability of selecting a boy given that the newborn is boy. So this is the case here. Okay. So this is what we have. Okay. So this will be like half times 4/7. And similarly, this will be half times 3/7. Right. So this is how much? So this is like you have 14 here and then 7 on the top. So this comes out to be half. Okay. So this is what we have calculated. Now what we are asking for in the question is the following. What is the probability of that the newborn is a boy given that the selection was a boy? This is what we want. This is what we want. Okay, so now what do we know? So let us see this. So we know a few things like conditional probability we know. So the normal definition what we know is N intersection B divided by probability of B. Probability of B we calculated here. Okay, so this is known, and this is also is known. B intersection N is also known, right? So this is like half and 4. So this is like N intersection B, right? So this case, this case, half of 4/7. Okay. Okay. Yeah, so this is like half of 4/7, and then probability of B we calculated. This is like half. So this turns out to be 4/7. So 4/7 would be how much? 557. Okay. G is 0.557, which is 57% chance. Okay. So what do we learn from here? What do we learn from here? The problem. So yeah, it's important to think about this, right? What happened? Like why it became 57%? You see, the statistician chose so statistician has chosen a boy. Okay, so he randomly picked and it came out to be boy. So how come the probability that that the newborn was a boy increased now? Can you see this? You see, like it's about, I mean, it's about thinking a little bit here, like, so the probability that boy was born increased, right? So, and I can ask the same thing, like what if the statistician randomly selected a, let us say randomly he picked, and if it was a girl, then the probability that the girl was born would have been again 57%. Okay. So what is happening here is also with respect to the timeline, right? Like January 1, everything was equal. Okay. And then there itself, you would have said, well, we don't know. It's 50-50, whether it's a boy or a girl. Right then, January 1. But then statistician comes on January 2nd, and he randomly picks, and he finds it to be boy. So then the probability that the newborn was a boy increased now. Okay. It increased now. And same thing would have been if it was, he would have randomly picked a girl. Then the probability that newborn was girl has increased now. So what you observe randomly in the present gives you an indication that what was more likely yesterday, right? So what you let us say you randomly do something, and then what you observe today will tell you what could have been yesterday. Okay. This is like very high level intuition I'm trying to give you. So the fact that yeah, you see a lot of pollution today, it could be that, yeah, it's effect of something that happened yesterday, right? So the probability that something happened yesterday increases more, right? So the effect, so you can get a cause of that, right? So what cause could have led to what you are observing today, right? So so the probability of that could have been higher. So this is what intuitively it tries to say. Now the question is, what if we try to solve the general problem where, let us say, there were k girls, okay, and k could be like arbitrary, we don't know. Like what if we start with a bias itself, like 3 boys and k girls, okay? So k could be greater than like 100, 1,000, 10,000. Like, does it really affect our result? Okay, that's what we are trying to say. Like, does it really affect our result if we do a k? Okay. So we can try to do this general case also. Okay. So let us try to do the general case. Okay. I don't know if I have. Yeah, I have one more thing. Okay. So let us try to do the general case, right? So in the general case, what do we have, right? We had, let us say, 3 boys and let us say G girls, right? So now we solve the general case. Okay, so G girls, assume G girls, okay? So we start with G girls and 3 boys. Okay, and then we always try to do this tree thing, because this allows us to quickly calculate things. So the one option is like G girls and 4 boys. So let us say the child born was boy, so it increased the boy, and let us say the child born was girl, so increase the girls, and then 3 boys. Okay, so if I compute the along this branch, then this is half of 4 divided by G plus 4, and along this it's half of 3 divided by G plus 4, right? Okay, so we can go ahead with the same plan like before. So we want to calculate probability of B. So the events B and N are defined as before. So this will, if you do the calculation, then this will turn out to be how much, right? So this will turn out to be how much? So it's like we have to add this, right? So if we add this, then what do we have? It's 2 and 1.5. So 3.5 divided by G plus 4. So 3.5 divided by G plus 4. And what we want to calculate is probability that the newborn is a boy, given that the selection was a boy. Okay, so this is probability that newborn is boy intersected with boy, and then probability that it's a boy. Now this is now N intersection B, right? So can I like already ask you in advance, what do you think will be this probability? Can you answer this in the chat? So what do you think is this probability going to be that I'm going to calculate? Okay, so no, result is not affected. Slok is saying that. Meghna is saying, shouldn't it be 2/7? I don't think so. Mehul is saying it's 4/7. That's correct. Same as before. Urmila, Mayank, 4/7. Shivam, 4/7. That's right, guys. So this is 4/7 because G by 4 will cancel out anyway, right? So if we do this, then so what we had selecting this is like this goes in the denominator, and what is above is like half of 4 divided by G plus 4, and divided by probability of B is 3.5 divided by G plus 4. G plus 4, G plus 4 goes away. Okay, and then what we are left with is because yeah, so you are left with 4/7 because 3.5 times 2 is 7. So this is again 57.1% if I write it in the percent form. Okay, so what do we observe from here? What we observe from here is the probability is not going to even change, given that regardless of how many girls were there initially also. Okay, that is not really changing our probability that the newborn will be the probability that the newborn will be a boy is still 57%. You see, yeah, you see what is happening here. So girl could have been million here. Okay, let us say million girls were there. Okay, and there were 3 boys here, but our probability is not going to increase because probability that a child will be a boy or girl remains 50-50. Okay, and then the statistician is picking has picked a boy randomly. So girls, the initial value of very high number of girls is just a offset. I mean, it's just a constant offset. Okay, it doesn't really it's a constant offset here. Okay, so that doesn't say anything because that data doesn't influence the fact that it's a 50-50 chance that the branching will be a boy or a girl. Okay, if we would have assumed something prior that okay, statistically it is observed that usually there are million girls than boys. Okay, then things are a bit different because then okay, you will say okay, maybe it's because statistically girls could be more chances of girl being born could be a lot more than boys and so on. But this initial statistical data is just a data. Okay, it's really not influencing anything at all. Okay, so that is why we don't see its effect anywhere. Okay, we still see it's a 57% chance. Okay, if someone would have given some prior, okay, then things might have changed. Okay, so the only thing prior was like the statistician have chosen a boy in future, okay, on January 2nd. Let us, I mean, future past, like it depends, like let us say current, and then it tells you what could have been in the past. Okay, it is very like now your chances that the boy was born was very likely because statistician has picked something randomly. Okay, but if there were G girls, then probability that statistician would have picked a girl would have been higher, right? Because there are like million girls, let us say, and let us say even if boy was born, there was 4. But then relative to January 1, right? So the fact that the boy would have been born, the chances are still like increased to 57%. Okay, so you think about these things. Okay. Okay, so now let us go to some other problem. So let us do some other interesting problems so that we can solve variety of problem. Like the girl boy problem, you can change this to balls. Okay, let us say in a box there are 3 blue balls and then k number of let us say red balls, and then you pick a ball and then you put a ball randomly there, whether it's a red or thing, and then someone picks randomly and he reveals you that it's a boy. Okay, it's not boy. It's a let us say blue ball. Okay, then what is the probability that that the someone that put the ball was a blue ball? Okay, so this same boy growth problem can be written in a very different forms. Okay, but you see, if you see types of problems, then you can immediately see where how to solve, right? So if the probability of seeing a car on the way is in 30 minutes is 0.95. Okay, so this is a slightly different flavor problem. So let us see what to do. If the probability of seeing a car on highway in 30 minutes is 0.95, and what is the probability of seeing a car on the highway in 10 minutes? In 10 minutes. Okay. So what we really want is, let us say P, which is the probability of seeing a number of cars. And if here we assume a constant default probability, in the sense like there is no such thing as like peak after 10 minutes. So from 10 to 20 minutes is very high, and no, we are assuming some constant number of cars per minute and so on. Okay, so this is assumed here. Otherwise, it's not possible. Okay, to solve this. So assume this thing. Okay, so probability the number of cars in 10 minutes. So this is what we want to compute, and the probability that we have number of cars in 20 minutes. Probability we have number of cars in 20 minutes, okay, is what, right? So probably the number of cars we have in 20 minutes is, so here since we assume this constant default probability, this will, in this case, it will be like the product of the probabilities. So it will be like P times P, the probability that I see number of cars in 10 minutes, and then probability that I see number of cars in the next 10 minutes, and so on. Okay, so in this case it will come out to be P squared. Okay, because they are like, yeah. I have not introduced formally the concept of independence, but we are trying to solve this intuitively right now. But I will define independence and then concretely tell you. So in this problem, we can go ahead and solve using, so again this will be like p square times p, and this will be p cube. Okay, so probability so probability that I see a car in 30 minutes. Okay, the probability that I see a car. Yeah, the probability that I see a car in 30 minutes, that is given to us actually. Okay, that is given to us. So oh, okay. Let's see how to solve this. I'm figuring out how to solve this. So probably the number of car in 20 minutes is, let us say, p square. Probably the number of car in 30 minutes would be p cube, and probability that number of cars in what we want is probability. Okay, what I can do is change a little bit. Okay, so let us say I change this to no car. Okay, so no car, let us say no cars in 10 minutes. And probability that I don't, there are no cars in 20 minutes would be p square. Okay, so let us say no cars in 20 minutes. Let us change this, and then no car in 30 minutes would be p cube. Now, now the probability that that I get a car in 30 minutes. So car in 30 minutes would be 1 minus probability that I have no car in 30 minutes. So this will be 1 minus p cube. Okay. So
shouldn't it be 1 minus p whole cube?
So this is like no cars in 20 minutes. So total is like p cube.
Oh, sorry, sir. P is no.
Yeah. So if I expect a car in 30 minutes, then it's 1 minus p cube. So car in 30 minutes is given to me. So this is like 0.95. So from here I can solve for p, which is square cube root of 0. No, I mean there is a 1 also involved here, right? So okay, so p is like 1 minus of that. Okay, so okay, so the p will be like cube root of 1 minus 0.95. This is like cube root of 0.05. Okay, and now car in 10 minutes will be 1 minus. So p we got, right? So p is what we need. So now we got a p in terms of those 10 minutes, right? So now now the probability that I get a car in 10 minutes is 1 minus probability that I don't get a car in 10 minutes. This is what was there, right? And this we calculated. Okay, So this we found, right? So this will be, we have to solve this cube root thing, and then we can plug in here. Okay, let us recap what we did. Okay, so this is a problem slightly different, but it's okay. So the question was, if the probability of seeing a car on the highway in 30 minutes is 0.95, what is the probability of seeing a car on the highway in 10 minutes? So the way we started with is probability. Let us assume that the probability P is the probability that I don't see car in 10 minutes. Okay. Then the probability that I don't see car in 20 minutes, because there's a constant default probability. So from 0 to 10 minutes and 10 to 20 minutes, it's like the, if I don't see it, then if I go further in that branch, then I don't see it again. So with the same probability P. Okay. So it's like P branch, and then I go further ahead another 10 seconds. So this is like 10 minutes, I mean, another 10 minutes with same probability P, and so on. Another 10 minutes with same probability P, and so on. So after 30 minutes, I don't see a car is like is like P cube. Okay, if you see this in as a branch. Okay, so so that's why it's P cube, that I don't see a car. And and then from there I can get the probability that I see a car in 30 minutes, which will be 1 minus P cube. So which is given to us as 0.95. So we solve for this, and then we get get the value of P. Okay, and then but P was no car in 10 minutes. So from there we get car in 10 minutes to be 1 minus P. Okay, you could have solved this also even in a slightly different way. Okay, but yeah. Okay, these are some miscellaneous problems, just to not just Bayes theorem, but also in general about probability. So let us see this problem. Standard dice has 6 showing with a probability of 1/6, which is the same as every other number. So if you look into the standard die, then the probability. But let us consider skewed die. So a loaded die or skewed die has 6 showing with half the probability of other numbers. Okay, so the probability that I get a 6 is now half, and the probability that I get, let us say, 1 is some probability, right? So probability is half of the others. So let us say others are like P. So then this is like P by 2, right? So probability of 2 is P, and so on. So probability of 5 is P. Okay. So now the question is asking, so this is what we wrote, right? So probability of 6 is half of the probability of the others, but we are not told what is that P, right? So this is not being told to us, but still we want to know what is the probability of rolling a 6. Okay, so how do I compute how do I compute the probability of rolling a 6? Can you answer this in the chat? So what do you think? What should I do next to find P? Akash, P plus P, what do you mean by P plus P? So, okay, sometimes I forget to scroll down. Okay. So what do you think? A small doubt, what we're assuming? Constant default. Yeah, for the last question, constant default probability was like number of cars you see in probability that of seeing certain number of cars in between 10 minutes, and from 10 to 20 slot is the same. Okay, that's what we mean by constant. Okay, so Slok is saying like sum to 1. Okay, so probability sum to 1. That's what we are trying to say. Okay. Because these are the so this is the probability axiom 1, right? Probability axiom 1, you recall this. So probability of the sample space is 1, right? So in our sample space we have what, 1, 2 and so on up to 6. These are the all possible outcomes when I throw a die, and probability of sample space is 1. Okay, and they are like mutually exclusive, so sum of the probability must equal to 1, right? So this is like p by 2 plus 5 times p, okay, is 1. Okay, so from here you can solve for p. Okay, so yes, so we have used probability axioms to solve this problem, right? Even though explicit probabilities were not told to us. Okay, let us consider a spam email problem. Okay, so let us consider this. So this is in line with the Bayes theorem. Okay, so let us try to solve this. So it is estimated that 50% of the emails are spam emails. Let us say half of the emails are spam. So this is a problem that we started with in the last class, I think, last class, I think. So, but this is a slightly different problem, right? Some software has been applied to filter the spam emails before they reach your inbox. A certain brand of software claims that it can detect 99% of the spam emails, and the probability for a false positive, that is non-spam email detected as spam, is 5%. So there is a probability of false positive which is 5%. Now if an email is detected as spam, then what is the probability that it is in fact a non-spam email? Okay, so these are the typical Bayes theorem problems. Okay, so let us try to solve this. Okay, so let us try to solve this. So we need to define some events. So let A be the event that an email is detected as spam. Okay, so email is detected as spam, and B be the event that email is spam. I mean the email is detected as spam and the email is spam, so it's like, I hope it's not confusing here. And then B complement is event that email is obviously not spam, is not spam. So the reason why these two are different is one is like detected as spam, and another is like it is a spam. Okay, so there is a difference between these two events. Okay, so what is probability of B? Probability of B and including probability of B complement will be half, because 50% of the emails are spam. So it's a 50% possibility whether an email is spam or not a spam. So that's the thing. And probability that A given B. So what is the probability that email will be detected as a spam given that it is a spam? So that is like 0.99%. Okay, I mean 99%, which is 0.99 in probability, and probability of A given B complement, so which is just is like yeah, you cannot say that this is 1 minus of this. Okay, so this is actually given to us. So probability of A given B complement is in words is 1. So probability that an email is detected as spam given that email was a non-spam. Okay, so what is this? This is actually the false positive case. Okay, this is like a 5%, so it's like 0.05. Okay, the probability that the email is detected as a spam, although it was not a spam. So that is like false positive. Okay, it was not positive. Okay, it was not really a spam, but you flagged it as a spam. So that chances of happening are 5%. So it's 0.05. And what we are supposed to calculate is probability of B complement given A. So what is the probability that it is a non-spam email given that it is detected as a spam? So this is exactly what we want to calculate. So this is probability of A given B complement. So this is the base rule, probability of B complement divided by probability of A given B, probability of B plus probability of A given B complement. So this is the total probability. Okay, so if we calculate this, then this comes out to be 0.05 times 0.5. Probability of A given B is like probability of B is like 0.5. Okay, so probability of A given B is like 0.99. Probability of B is half. Okay, so it's 0.5. Okay, so this is like times plus, and then probability of A given B complement is 0.05 times, and probability of B complement was again half. So if we solve for this, okay, then we will get some answer here, right? So this is a standard application of the Bayes theorem. Okay, so I did this again for for a practice. Now, okay, so okay, so now we have a attendance quiz, and this will be graded. So you log on to this URL, and you will have some problems that uses Bayes theorem. Please attempt this quiz on the link above, and yeah, so and then I'm going to start the timer. So I hope that this link is working. If not, then please let me know, because sometimes it happens that it doesn't work. I mean, for whatever reason. So
Sir, it says it's not accepting responses.
Yeah, same for me.
Okay, so that's very strange. Okay, let me open this and check again why it's not accepting. Okay, let us do one thing. Let us continue with this quiz in the next class. Okay, so we can do this quiz in the next class, because right now it's already 10:26. Time is very less now. Okay, so I would like to stop here and continue in the next class. Okay.